Good morning, all. I welcome you all for this session that is on lumped heat analysis, so which is a heat transfer process. So it is comes under transient heat conduction heat process or unsteady state heat process in which temperature will be varies with time. So the examples for temperature variation with time will be one example will be heating of the surface of the earth or cooling of the surface of the earth during daytimes and during night times heating and cooling of the earth surface will happen. So due to that temperature will be varies continuously with the time in a day. Similarly, in icing instant due to combustion cooling of the engine cylinder, the temperature of the engine cylinder surface will be continuously varies with time. So these are the two examples of transient heat conduction problem. Next one is coming to this now, lumped heat analysis now. Let us take one solid will be cooled in an environment. Let us take a cylinder. Let us take a hot cylinder, which is cooled in a cooling medium. So here now, the resistance offered by the heat flow will be called as internal resistance and internal resistance. Next one is the resistance offered by the convection now surrounding air now, that is called as conductive resistance. So one is called as internal resistance, one is called as surface resistance, or it is also called as conductive resistance. If it is very negligible, if it is very small when compared to surface resistance or convective resistance, no, then that kind of study is called as lumped heat analysis. Lumped heat analysis. So lumped heat analysis means it is a heat transfer process in which we are assuming the internal resistance or the conductive resistance is negligible when compared with surface resistance or conductive resistance is called as lumped heat analysis. So when a resistance is there is no resistance inside the solid. When there is no resistance in the solid means the spatial variation of temperature is negligible. Spatial variation of the temperature will be negligible. When space variation of temperature is negligible means temperature throughout the body will be uniform. The uniform temperature will be varies with time only. The uniform temperature will be varies with time only. This is the main feature of lumped heat system. So in lumped heat analysis, what we are doing is, if time is given, we can find temperature. We can find if time is given, we can find temperature, or when final temperature is given, we can find what is the time required for final temperature during heating or cooling process. Next one is generally, in metallurgical process, in metallurgy, you will find many heat transfer problems requires understanding of the complete time history of temperature variation. So in metallurgy, now there are process will be there like annealing. Next one is quenching process will be there. Annealing, slow cooling can soften the metals and improve the ductility, whereas quenching means rapid cooling, which can harden the strain boundary and increase the strength. So this is the governing equation for the unsteady state heat transfer problem, where alpha is called as thermal diffusivity. When alpha is very large, means heat will be diffused into the material at fast rate, or when alpha is less, it will be diffused into the material at a slow rate. Next one is I told you, temperature throughout the body will be uniform in lumped heat analysis. That means at center you will get the same temperature. At any location also you will get the same temperature. On surface also you will find same temperature. That is the concept of uniform temperature throughout the body, which is in lumped heat analysis. Next thing is the validity of the lumped heat analysis will be decided by byte number. Byte number is the ratio of two resistance. One is called as the internal resistance. It is called conductive resistance. It is given by L by Ka, and the other one is called as convective resistance and or surface resistance. Now that is called as 1 by Ha. So Ha and Aa will be get cancelled. We get HLC by K, HL by K, or since there are different geometries will be there, it is called as HLC by K, where LC is called as the characteristic length. So different geometries will have now. So we'll calculate the characteristic length for different geometries. We will see later. Next one is when byte number is 0, when byte number is 0 means conductor resistance 0, the body is termed as isothermal. When byte number is small, conductor resistance will be less, the body is still approximately isothermal. Next thing is here now, when for small values of byte number only, we are applying the Lambert capacity analysis can be performed. When byte number is large, so conductor resistance will be significant, and we cannot apply the Lambert analysis. Here we are using a Heisler chart solution, HEISLER, Heisler chart solution for solving this kind of problems, where resistance is considerable amount will be there. So if you see, for example, now a cylinder is there, which is kept in a hot air. So what will happen? Heating will be happen. So after a certain time now, what will happen? The temperature of the throughout the body will be uniform. It is called as lumped heat analysis. When temperature will be varies with time now, that is called I'm sorry, varies with distance. Varies with distance now, that is called as byte number will be very large, very high. Byte number is high. When byte number is small now, temperature will be uniform or same throughout the length. Throughout the length. So that means in the heating process and cooling process for a given H value, when we can find temperature for the given time, or we can find the time for the given temperature in case of a Lambert analysis. So this Lambert analysis will be applied only for only when byte number is less than 0.1. That means when byte number is less than 0.1, then only we will apply the Lambert analysis. This is the applicability of or validity of Lambert analysis. Next thing is we will see the a small derivation here. So here amount of heat transfer, heat transferred. Let us take that this is the given body. These are the m is the volume, m is the mass, v is the volume, rho is the density, Ti is the initial temperature. So suddenly it is kept in A is the surface area. Suddenly it is kept into the hot air. H and T infinity will be the convective heat transfer and the temperature of air. So here now Q convection is equal to increase in heat, increase in increase in energy body, that is given by HA into T infinity minus T will be the convection process. Increase in energy body due to kept in a hot air, now MCP dt by dt will be given. So here M can be written as rho V. Therefore, we can write, if you send this side now, HA by rho V, HA by rho V into HA by rho V into T minus T infinity is equal to dt by dt. Or we can write dt by T minus T infinity is equal to what is that? HA by rho, here Cp will be there, rho Cp Vv into dt will be there. Or we can write dt by this is T infinity minus T infinity minus T, and here if you make T infinity minus T means T minus T infinity means you will get extra minus sign, that is called as HA divided by rho CPV. Here dt will be there. So now you integrate this equation, you will get this will be ln of T minus T infinity is equal to minus HA divided by rho CPV. So integral of dt will be T only, integral of dt will be T only, therefore you will get T only. So integral of dt will be, this is called as T, this is constant, now we can take out of the integration, you will get this value, plus C1 will be there. So in order to find C1 now, we are using, in order to find C1, we are using this initial condition. The initial condition is our time T is equal to 0, temperature is Ti. That means in place of T, Ti minus T infinity is equal to minus HAT. T we are putting 0 by rho CPV plus C1. So this value will become 0 and you will get C1 is equal to, what is it, ln of T naught minus Ti minus T infinity will be there. So the final equation will becomes now, here I will write the final equation, that is ln of T minus T infinity is equal to minus HAT by rho CPV plus ln of result you will get ln of Ta minus C value will be Ta minus T infinity. Send this side, this one now we get log A by log A minus log B. Log A minus log B now we will get this form, that is ln of T minus T infinity divided by Ta minus T infinity is equal to next one is e power minus HA by rho CPV T will be there. Suppose if you send ln that side now, the equation will becomes T minus T infinity divided by T naught minus T infinity is equal to e power minus HAT by rho CPV. This is the equation we are using for finding the temperature for the given time, or final temperature for the given time, or time for the given final temperature. Like that we are doing. Next one is this is the value of the B value. This is the B value. So when B will be increasing, with the what is happening now, the temperature of the body approaches the ambient temperature in T infinity exponentially. The temperature of the body changes rapidly at the beginning. A large value of B indicates that the body will be approaching temperature at a shorter time. When B value is very high, means with the shorter time only it is reaching the T infinity temperature, T surrounding air temperature in case of uh, heating process. Next thing is heat transfer rate formula will be at a given time. If you want to find heat transfer rate, means this is a formula HAT delta T minus T infinity, temperature of the body at the given time. Suppose in between, if you want to calculate the temperature for the given time, in the intervals of 0 to T means MCP, this will be the final temperature, and this will be the initial temperature. So this difference will give the total amount of heat transfer rate between 0 and T, initially and final. Next one is the for maximum temperature now, that is given as MCP T infinity minus Ti. So initially now Ti will be there. After final temperature, that is ideal case where it reaches T infinity. So this value will indicate the formula for Q maximum. Next one is in byte number now LC will be there. LC is called as V by A. LC is called as V by A, and that is called as HLC by K. And byte number is called as Lambda also will be applicable only when byte number is less than 0.1. So I told you now for various geometries LCs will be there. For flat plate of thickness L now, LC is V by A, that is to LBH. This area will be two sides, front side and back side for the wall. So this thing will be get cancelled. You will get L by 2. For cylinder now, pi r square L and 2 pi r L will be there. Pi r L, and you will get R here. You will get R by 2. For the sphere now, 4 by 3 pi r cube and 4 pi r square. Pi r square and pi r square will be get cancelled. And 4 and 4 also get cancelled. You will get R by 3. For cube now, volume is L cube and surface area is L square, 6L square. Therefore, the L square and L square will be get cancelled. You will get here. So finally, the characteristic length will be LC. So this is about the lumped heat analysis. Thank you for watching this video. If you like this video, please comment and share and subscribe. So my name is Hari Prasad. This is my WhatsApp number and email ID. If for any doubts and for any clarifications, for any problems on this lumped heat analysis, feel free to contact me through this WhatsApp number and email ID. Thank you for watching this video. Thank you.